Welcome to the first content module of Foundations of Machine Learning called Models, People, and the Road Ahead. So we'll talk about a few things in this module, mostly just laying the foundations for the rest of the course. So I want you to think of this, this particular scenario where we have AI deployed in a hospital or clinic setting. Imagine this hospital. There's an algorithm that is being used to decide who gets extra care or any care at all, and who gets less care or who gets sent home. So imagine two patients present and they're equally sick, but the model ranks one high risk and the other one low risk of complications, of things getting worse. And then therefore the decision is made to only provide extra care for the former, for the first person who's high risk. So how could it be the case that two individuals who are actually equally sick have different outcomes in the hospital? So this is actually a true story. I'll link to the paper in a moment. Researchers in this situation, not the exact one shown, but the one that was described a moment ago, discovered that this AI model that was helping to assess for the risk of the patients wasn't actually predicting on risk, on sickness at all. What was happening is that the model had learned that there was a correlation between how sick somebody is and how expensive it is to treat them. And then therefore, it found that that was the cost was an easier measure to predict, and it ended up predicting future healthcare cost instead. Now, because cost reflects more than just sickness, but it also can be related to access to healthcare in the first case, spending patterns, and so on. So not just illness. It turned out that in the actual health data, in people of color had less access to healthcare, so they ended up having less healthcare, and then therefore the costs of that healthcare were lower. So from a certain point of view, you could say that, well, this person, because of their demographics, I don't expect them to cost very much. Therefore, their risks are not very high. So all these features that correlated with each other painted a picture that was not really correct. Like these two individuals were actually equally sick. So this paper, which you can read about down here at the link, showed that if you fix the target better, then and you kind of remove the effect of cost alone, you could have increased the share of Black patients flagged for extra help from just 17.7% to around 46.5%. So more than double the rates at which they were seen, which is important. So a hospital used an algorithm to decide who gets extra care. It looked very accurate. So in validation, on paper, so to speak, it looked very accurate. But it was actually predicting the wrong thing. There were all these confounds in the data. So it was actually predicting something that we didn't expect. So cost is a proxy. That means it can stand in for something else that reflects various things like access, spending patterns, and that's what ended up complicating the system. So I want you to take a moment and in your journal of choice, think about this question. If the metric looks great, so like the accuracy you're getting on some validation set, I think you know what that means, but the accuracy or the overall performance of a system, say, like how do you recognize that this happened? How would you recognize that this problem exists? So here's another example. In this case, there's a self-driving test. An autonomous vehicle detected a pedestrian. So in its sensors, it saw that there was an entity there. But it never classified her as a pedestrian. So it saw that something was moving, but it wasn't sure if she was a bike or something else. I'm not sure. But she wasn't classified as a pedestrian. So 5.5 or so seconds passed, which is a long time in a car. And there was a fatal impact, resulting in death. And the design, in a subsequent analysis, it was found that the design precluded emergency braking, so it relied on the human operator to step in and intervene. So here, again, you can click on this link and read more about it. So this is obviously a problem also. I mean, it might take a human more than 5.6 seconds to really understand what the situation is in the first place. So, the system tracked the pedestrian appropriately, so part of the system worked as intended, but the classification part, the part that said what this entity actually should be labeled as, pedestrian, bike, something else, didn't work quite well. And moreover, the decision policy, so what to do with this scenario, there wasn't any sort of emergency brake in the situation. You can imagine an alternative where when a car detects something in its path that it can't classify, do the safe thing and just do an emergency brake just in case that thing you can't classify happens to be a life form. That's one way of doing it, putting up what we call guardrails around a system so that really negative consequences don't happen. Here's another thing to think about. If the perception part, the part that identified that there's something there, works most of the time, what kind of safety layers can we put into place that can prevent a rare miss from becoming fatal? Okay? And moreover, I want you to think about, can you always rely on guardrails? We'll come back to these topics later in the class, but it might be the case that that just merely putting some code and having an emergency brake in this case might work in some situations, but it might not work in others. So think a little bit about situations where one part of the system works and the others don't, what we can put in place in order to make things safe, but also whether or not what we put in place is actually robust. So, foundations. These are kind of alarming examples, like real-world, actual examples that resulted in unequal healthcare and fatality. But obviously, those are to some extent shocking, but that doesn't represent AI as a whole. AI is often used correctly and for benign reasons and can actually help solve many of our problems. Now, the issues include that machine learning is quietly, and sometimes not so quietly, being implemented almost everywhere. So what you see online, what transactions are flagged by your bank as fraud or not, who gets loans, who gets admitted to a university, which patients get care or not. These are all like real-world deployments of machine learning currently. And as we use foundational machine learning and add extra depth, so to speak, and we apply deep learning techniques, then we can do a lot more, right? We can translate between languages, generate videos, including deepfakes. We can write code. We can power chatbots in ways that just weren't possible even just a few years ago. These systems are getting very complicated, and therefore they're getting more inscrutable, which means essentially they're like black boxes. And the more complicated they get, and the more their complexity sort of evades our understanding, the less we'll be able to diagnose when problems occur, like the ones I mentioned a few moments ago. This class is basically about giving you X-ray vision, so to speak, into these black boxes. So it's not enough just to know how to use Google appropriately or how to get your favorite chatbot to respond in the way you want. We need to do better. We're going to actually seek fulsome, deep careers in machine learning. So basically what we want is to be able to turn vague ideas or use cases or tasks into something very precise, and then therefore something that we can represent mathematically. We'll use optimization to model data that we obtain from the world, and then we will be the best scientists and the best engineers we can, and we will do science and ship models in a way that general users won't be able to. So by the end of this course, you should be able to look at a new machine learning paper, a new bit of code or a model. You'll be able to read a news article or a post about machine learning or AI, and you'll be able to understand more than the general population. You'll understand the assumptions, you'll understand how the model must have been trained, you'll understand how you can test it and look for problems, and you'll also understand kind of ethically to some extent how this could be defined as a bad idea. For this module, I assume you've already watched the M00, so you know how the course works. You'll be able to explain in your own words what machine learning is and how it differs from traditional programming. You'll be able to, at least at a very high level, map a real-world scenario from data to modeling to a metric to a decision, and then to think about stakeholders. And you'll be able to articulate, to some extent, the math background that machine learning actually requires. So, machine learning and deep learning in the world. So every day, models are, ranking posts in your feed, performing all these tasks I mentioned a moment ago. All of them, even Google searches, which is a form of AI, like I mentioned, follow a similar pattern. They all take some input, which we'll label X, and then they produce something, some kind of output, which we'll call Y. They could also produce sort of a score, like a ranking, like a probability or a confidence, which we call P hat. To do this, to map from inputs to outputs, machine learning is these models are trained on data in order to do this as well as possible for some definition of well. So we're going to learn how to build, stress, test, and reason about these systems. Here is an image of sort of a kind of standard use case we see in early machine learning courses, where we upload, say, videos or images. So in this case, input X could be this image. And then we want to get some kind of output as to a label for what this image is. I mentioned we can also get a score, P hat. And over here you can see, there's a certain chance or probability that a tag associated with this should be a flower. There's a certain probability, or so to speak, that it should be a plant or a petal and so on. So you can see how each of these labels here are associated with different scores, P or P hat. So this came up just a few weeks ago where I was in a multidisciplinary setting, and individuals in that setting kind of thought that AI was what you and I might call agents or chatbots, and other forms of what I would call AI, like speech recognition or machine translation or lookup, was something else. And that isn't really the case. So I think the standard definition for how all of these concepts relate to one another can be found in this book by Goodfellow, Bengio, and Courville. It's basically kind of a set of increasingly focused definitions. So AI is any system that appears to act intelligently, even systems that are explicitly programmed by a person to do so through like a if-then-else code that is meant to represent their best solution to a problem. So you don't even have to do machine learning in order to do AI. Machine learning is a subset of AI, so it's still a system that appears to act intelligently, but it does that by learning from data rather than from explicit rules. Sometimes this data has been kind of massaged for us already, so we don't get raw images necessarily in all of machine learning. Sometimes we get statistics or what we call features that are extracted from the data. So we don't just get a picture of a flower, but we get a statistic, like this is the length of the petal or the average length of the petals. These are the average widths of the petals, and so on and so on. So we did some pre-processing and information gathering between data acquisition and actual modeling. Representation learning is a subset where actually we can forego with the pre-computed features. I don't care about having a person guess at the lengths or having a bit of code guess at the lengths and widths of petals. Just give me the raw images and I will learn, whatever internal representation I need to do, modeling properly. Or I, in this case, is the model. And deep learning is a form of representation learning where we do that, but we have multiple layers of abstraction. So maybe we're not just measuring lengths and widths of petals, but we're also measuring how they relate to one another, what angle they're in, how they relate to one another, how they relate to the background in a scene. All of these are different levels of abstraction, usually found within the different layers of a deep neural network. So in this course, we'll start with core ideas. So it's important not to just jump straight to transformers, generative or otherwise. We want to get the foundation straight so that we can understand how to deal with cutting edge first. So we'll start with some ideas like supervised learning, maximum likelihood estimation, risk, and regularization. We'll go through some classic models, which are still very useful today, like linear models, principal components analysis, and kernels. And then we'll wrap up the entire course with deep neural networks and transformers. And these will still rely on the foundations we learned throughout the rest of the term. I welcome you to just kind of click through this link. It's a little demo where you can play around with a synthetic, fake data set of circles and moons and other shapes. You can change various aspects, so you can interact with it through my slides also. You can kind of change what the data look like. You can change what kind of features you're extracting. So this is sort of this is a kind of short-circuiting the representation learning. So I'm saying I want horizontal or vertical differentiation, or I want different shapes. I want a sine shape In my feature space, you can change the number of hidden layers. You can change the number of neurons per hidden layer. And then each of these are going to give you an output where we have things called losses, which we'll define soon enough. And we kind of classify the orange dots from the blue dots. So please click on this. It's a fun little website. Another fun website that is visually fairly beautiful is this Visual Introduction to Machine Learning. So they built a decision tree to distinguish homes in New York from San Francisco. New York is like Toronto. San Francisco is like Vancouver to some extent. It's in the US. So this is, they deal with training versus test data, which we'll become familiar with. They deal with splits and overfitting, which we'll talk about. And they'll talk about bias variance trade-offs, which will also be important to us. So they frame it like a graphic novel. So scroll through this. This is only a screenshot in this case, but you can click here, follow through it, and just get familiar with the beauty of machine learning and data. What is machine learning? So traditional programming, like I mentioned earlier, some forms of AI could have just been traditional programming, where we would have maybe we're working in a bank. We have to figure out if someone should, when they make a withdrawal, can they, do we allow it or not? And then we'd write, using our banker knowledge, we can know that if the balance in their account is greater than zero, so they have some money in their account, and they're not overdrafting, so the overdrafting is false, then go ahead and allow the withdrawal. This is the kind of static code that individuals used to write in old AI. The computer will just follow your logic. So in machine learning, instead, we're going to have lots and lots of examples of inputs X and Y. X might include balance and overdraft and maybe some other features as well, and outputs will be just like whether or not withdrawals were allowed. Then we're going to choose a flexible family of functions, f sub theta of x with parameters theta. So just for argument's sake, a family of functions like the Gaussian curve, the normal curve, could be a family of functions, right? It has a certain shape to it. And the parameters of a Gaussian are its mean, mu, and its standard deviation, sigma. So we know this already, so I don't need to dig into it too much. So parameters theta is a set of subparameters mu and sigma respectively. And x would be all of the data that we want to fit these parameters in such a way that this function f sub theta of x gives me good predictions for what y should be. I mean, I wouldn't use a Gaussian necessarily to do classification, but that's just for simplicity's sake. Maybe we have SVM or a linear boundary defined by its slope and its intercept. Well, we'll talk about that later. For now, the details don't matter much, but they will later. So what we want to do is produce an algorithm that basically searches for the best parameters of theta that make the predictions match actual observations, y sub I, on training data as well as possible. So again, machine learning is turning vague problems, like be as accurate as possible on this bank-based use case, into a mathematical form like we saw below. Okay, we'll be dealing with functions, losses, optimization. All of these have a component to code and a component in mathematics, which in some sense are often the same thing. So Tom Mitchell defined machine learning as a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks T as measured by P improves with experience E. So this little graph over here is meant to be Mitchell's triangle. So take another example. Take spam filtering. We have a little AI that's sitting in your Thunderbird or whatever email client you use. The task is to just classify emails as spam or not spam. The experience is all of the data you've accumulated from emails that were previously labeled as spam or not spam. And then performance could be the accuracy of making this doing this task. Or it could be that we care more about false alarms than we care more about avoiding false positives than we do about avoiding false negatives. By which I mean, we'd mind less if spam occurs in our inbox, then we'd care about not spam going to our spam junk folder, right? because in the former case, you're just kind of annoyed, you just have to delete an extra email. In the latter case, you might miss something important. So like the performance here is something a bit more detailed than just accuracy. We'll talk about that later in this course too. So generally, we'll understand what the task is, we'll understand what data and experience we have and what we need, which is not always the same thing, and we'll measure performance to see how it's aligned with decisions and costs. So some key terms that you should be able to understand like fairly soon. First of all, a data table. Not always, but sometimes data takes the form of a table where the examples are the rows of the table and the columns are the various features, like whether there's a balance in the bank or not. Could be one column of variables in your data set. Features X is what the model gets to see. Label Y is what you want to predict. So technically, when you're training, you have access to both X and Y. But in practice, if you're deploying this, you'll only have access to X, and you'll have to make good decisions Y. A model f sub theta of X, like we mentioned, is a parametric function that we can evaluate. So it's parametric because it has parameters theta. It's not always differentiable, but as we'll see in a few moments, as we'll mention in a few moments, being able to do calculus on these functions is important, otherwise sometimes we wouldn't be able to do machine learning at all. A loss, script L or fancy L, is a function between the prediction made on a particular data point and a prediction. So this is more or less how bad a prediction is on one example. So remember, loss is bad to lose things, therefore loss is something we want to minimize. Empirical risk. Sometimes, to be honest, in the real world, when people say loss, they're really referring to empirical risk. But this is sort of the average loss you have over all of your training data. So loss is computed on one datum, one data point. Empirical risk is the average over the entire training data set. The training algorithm is what the method that searches for the parameters theta hat. So theta hat is like the best parameters you could find, trying to minimize the empirical risk. A metric is a summary of performance on held out data. So after we've trained a model, how well do we perform on held out data? And then down here on the right, you can see sort of the that whole process. A little example. So it's a toy regression example. We'll see. So the question, the kind of loose question is, can we predict a car's fuel efficiency from a couple of features about its car? So we'll produce some random data. So again, as will often be the case in this class, I'll provide code for you, and then you just copy it and run it in whatever environment you like. So I don't need to go into too much detail here, but what's going to happen is I'm going to create a random data set using the normal distribution with provided means and variances. I will estimate what the true hidden linear relationship should be between miles per gallon and these features, weight and horsepower, and I'll add a bit of extra noise just to make things a little bit more realistic. And then this is where I put everything together in a data set, in particular a pandas data frame. So we have weight, horsepower, which are X, our input features, and miles per gallon are our output. This would, more correctly be kilometers per gallon, but we'll take this as it is. So we have our data. So our data is printed up here. It actually is this is code that runs, and it's printed up here. So sometimes when you run this yourself, when you run this random number generator, you might end up getting different random numbers. Although it looks like I've kept that from being possible. But regardless, here's our data. This is one kind of car, another kind of car, a third kind of car, and so on. So, we'll talk in great detail about what each of these steps mean, really, but here basically I'm just splitting up my data, our small data set, into a training set, a test set. I'm choosing a particular kind of model called a linear regression model. I'm calling a function from the scikit-learn library. So scikit-learn has all kinds of different models, one of which is linear regression, and those models expose this function fit, which gets me the best prediction it can on the training data. And then I do prediction, which is basically testing on technically the test data, although here I also make predictions on the training data, which normally I don't care about, at least I wouldn't in terms of reporting, but I just wanted to show it just to flag it. And then I print up all of my statistics. So here the training mean squared error is actually higher than the test mean squared error. So we can talk about why that might make sense or might not make sense in future modules. And then also print out the coefficients. So the coefficients here mean the same thing as parameters. So the parameters of a linear model are basically the slope of that model. In this case, because we have two variables, it's a plane, not a line. So a plane will have a slope in each of those two dimensions. That's why the slope here is a vector of two numbers. And then the intercept, where this plane intercepts on the prediction. So if weight in kilograms and horsepower are both 0, we'd expect somehow the miles per gallon to be 61.6 approximately. Anyway, then we can print out our data. The scatter plot shows us the randomly generated data here. We have a line that's drawn through this data. And you can see it seems like the data more or less kind of falls on a line, although a lot of it seems to be above this line. So even in this very simple example, this totally synthetic example, we can see how we took some data to train the model and to derive the actual parameters or coefficients of the model. And then afterwards we did the testing. We did the prediction to see how well we would do on the held out data that we didn't use for training. We're already thinking about generalization. So always these models are things we expect to be able to use in the real world. And when we use it in the real world, it's going to encounter data it's never seen before, which is why it's so important to evaluate these systems on data that it never saw before when you're doing the training. It is a very simple model. So this is what we call a baseline. Like a linear regression might be one of the simplest models we have at our disposal. Sometimes it works very well. And we had a metric, which is a mean squared error to quantify error. This is more or less we'll return to this as well later. This is just an introduction, but it's sort of the average squared distance between the data points and the line that we've learned. So later on, you can ask yourself this now if you want, but are these linear assumptions reasonable? Should we have not taken a linear regression model? How do we have known if it's reasonable or not? What happens? What would happen if we added more features or a more flexible or complicated model? And I mean, we're getting ahead of ourselves a little bit, but how can we trade off bias versus variance? Well, if you don't know what those are yet, we'll define them later, so no worries. This is not marked. Just very briefly, we talked about academic integrity in Module 0, but I want to kind of mention it again here. So remember at the very beginning, the use cases we had were scenarios in which people could be approved for or denied healthcare, or where people could perish while they're crossing the street, right? So this isn't just a mere academic exercise, although that's also important. When we deploy these models, there's real-world benefits and real-world harms that can be the net result of this. So we need to think about fairness. So does the training data we have incorporate past bias, as it did in the healthcare example? A model can not necessarily always add bias, but can certainly amplify it. If we're measuring only accuracy across the whole population, is this kind of hiding maybe big differences across subgroups? Privacy is, of course, a big deal. Models trained on sensitive data can leak information. And then questions of robustness. So small changes in inputs. If you make small tweaks to our data and then the model changes wildly, then this model is not robust, right? It's not something you'd be comfortable deploying in any setting, really. You want things to be relatively controllable, containable, and deployable. Occasionally, you have a model that is still contained fairly well. So you did a lot of robustness checks, which we'll see throughout the course of this of 3151. But models can also be used in unexpected ways. So this is something that we need to consider increasingly when we're deploying these models. We always have to ask ourselves, who can be harmed if this model is wrong or if it's used in an incorrect way? And what evidence would you need before you truly trust the model? I want to talk briefly about falling in love with the math. So it might be said, and I hope it's said at some point, that this course is math heavy, and this is a very good thing. Okay? So we want this class to be math forward. Okay, we are going to see lots of API calls, and we're going to see some prompting of large language models later in this course. That is really important, and it's important to be skilled in those areas as well. But if that's all you can do, then you haven't really learned machine learning. You haven't really learned AI. To really learn AI, you have to be able to open up that box, and you have to see how the components work inside. And to do that, generally we need all of linear algebra, calculus, and probability. So vectors and matrices, derivatives, gradients, and optimization, and random variables, expectations, and conditional probabilities, respectively. I'll talk about that a bit more in a moment. So again, why is it good that we're going to do more and more math in this class? Math is clarity, right? So language is ambiguous, prompts are ambiguous, documents are ambiguous. Math makes things unambiguous. It forces you to state your assumptions, to be precise and specific in terms of the order in which steps are taken and how those steps are taken. It lets you actually produce new algorithms or diagnose algorithms, so to speak, instead of just memorizing that you need to make a certain function call, right? So math helps you do the correct thing. Math can also help you design new systems. So changing the loss function, I mentioned loss briefly earlier, this will change what the model is trying to optimize. So understanding it mathematically will really help you understand what you're learning. Regularization is a topic we'll define later, but whether or not you want to simplify models or not, to what extent you can incorporate prior beliefs, this is going to be something we can also build in mathematically. And then analyzing curvature in various ways will help us better optimize methods. So generally, we'll start with intuition, maybe even some APIs and some code. We'll define things more formally, we'll define things numerically, and then we'll put things into code. So it's not expected that you are going to be an expert in each of these things. In fact, I'm sure at least some of you saw that this course is math forward and maybe became alarmed. Okay, chances are some of you might be rusty on some of these concepts, and that's normal. Some of you might even still be, even if you're like really practiced in all of these topics, it's always good to learn more, right? Like math exposes itself to constant learning, which is fun and it's useful. So I'm going to recommend that you focus on certain subsets of math. So derivatives and gradients from calculus, including single variable derivatives, partial derivatives. That's going to be important because derivatives help us understand how to change the update functions for certain kinds of machine learning models. Vector geometry, so lengths, dot products, angles, projections onto a plane, so how vectors work in space. This is how we represent both the data and internal representations, so understanding vectors is going to be important. Matrices, so to some extent an awful lot of machine learning just involves multiplying matrices by vectors and matrices by other matrices. And often we'll be able to boil systems down, so to speak, into linear systems. So matrix A times vector X equals some vector B. This should make some sense to you. And then we'll also kind of refresh your basic intuition about eigenvalues and eigenvectors, how things stretch and in what direction, because the extent to which things stretch in parameter spaces can determine whether you're doing learning or nothing at all. So to some extent, like always, you're going to have to be proactive and you're going to have to want to do math, right? And it's not a hard thing to get into, right? Anyone can be good at math. I would recommend, if you have the ability to do this, to spend, as few as 2 hours, maybe even 4 hours, revisiting this topic, these topics, ideally this week, or maybe prior to the first week of lectures, and maybe into the second or even third week of lectures. It's not a huge rush, right? And indeed, this is something you should be doing, at least to some extent, over time. So you can go to free websites. I'm not going to promote any paid apps. There are some apps that you can download. You can use them for free, and then you can play with certain topics like derivatives, like calculus, like probability. Khan Academy and 3 Blue 1 Brown. These both have YouTube channels and other materials that you can use to just get refreshers on at least the intuition. Merely watching a video, the risk here is that these videos can be very slick and they're excellent. I think one risk is that we can watch a 10-minute video, kind of follow along, and at the end of it feel that, okay, I didn't feel confused through most of that. And that's a good thing. They don't become too confusing. But not getting confused by watching 10 minutes of a video is not the same thing as actually understanding that topic. So that's not necessarily going to be enough on its own. I really enjoyed just doing problems, so getting textbooks if you can, just free ones at the library, or going online for additional problems to solve. if you want, I can produce problems for you. So like I have like a bank and other faculty members here have access to math problems that I can kind of prescribe to you if you want. And generally, get involved, do the problems, ideally on paper if you can. So we're going to flag modules that depend on these topics, so I'm not going to suddenly throw a lot of math at you. And indeed, my intention is to slowly ramp up the math. So at first, you're going to barely notice it, but gradually the math will be so frequent and so clearly understood by you that it'll seem totally natural. So finally, not every module, but some of them will conclude with a quick check. So I'm not going to sit here and go through all of these questions, but you have access to these slides. So these are multiple choice questions. There's 4 questions here. Read them, answer them on your own, and some of them might refer actually to module 0, in which you didn't have a check-in. So do these, write them down in the notebook that we talked about before. Maybe it's orgrom, maybe it's obsidian, maybe it's paper, and then bring it to class. Before we go into module 2, make sure you do the module 1 quick check. Make sure you're already ready to run Jupyter locally or in the cloud. Be able to import NumPy, Pandas, Matplotlib, scikit-learn. I like having separate Conda environments for as much as possible. You don't have to have a Conda environment for every module by any means, but maybe create a new one for this class. You can also use venv if you prefer as a virtual environment for Python. I prefer Conda. Try to review your math, and at least even if you don't have to do tons of problems, I'm not necessarily saying you must do that, but just try to be a bit mindful of what you're good at and what you're soon to become good at, and just keep that in mind and let me know if you need help in derivatives, vectors, and so on. I would also like you to pick an anchor system. So whether you care about healthcare, whether you care about finance, any kind of use of AI in the real world, think about what you want to do with AI. Think about what you want to contribute. Think about what data you're likely to need to solve your problem. Think about what kind of decisions you could enact or make in the real world through these systems. And then also think a little bit about the kinds of risks you're worried about. These can be risks at any level. So at a very high level, I want you to think about this, and then we can talk about it in class. Our goal is to be able to do 3 things. We want to be able to think like a scientist, ship like an engineer, and decide like a leader. And often this will all be kind of intertwined with one another. Thinking like a scientist means not being satisfied with the initial answer, but being curious and probing, and always trying to do better, right? And being honest and being aware of limitations. That's all true of an engineer also. When we ship a product, we test it to a large extent. We don't make false claims about it. We make sure that it generalizes well. So like a scientific claim that works in one part of the universe should also make sense in another part of the universe. Like gravity works everywhere, for example. And similarly, like a product that you deploy in your lab in Halifax should also work in other cities, or indeed not even in cities as well. We're not here to just press buttons on a black box. So we don't want to just keep on playing with a large language model. We want to turn real world problems that can be very messy into math. We want to turn that math into models that we can build and debug. And then we want to be able to turn these models into decisions that we can defend, then we can take leadership on. I'm very happy to be part of this journey with you. Here are the references. On to Module 2.